So,
go ahead.
Okay. Thank you, Rochelle, for the introduction. My presentation is about the salt tectonics in the Eastern Persian Gulf in southern Iran, involving two tectonic salt layers and allochthonous salt. The cooperation of this group of peoples from Tarbit Mudaris University, University of Barcelona, and National Iranian Oil Company. So the content, the presentation comprises firstly a general overview of the geology and structure of the Eastern Persian Gulf in southern part of the Zagros Fold and Frost Belt, and then we will move on to look at some seismic profiles to look at the salt structures of this part of the basin, and then I will show you a few examples of cross-section restoration along some of these seismic lines, and then I will present two physical models that I have done at the Geomodels Research Institute of the University of Barcelona to understand some aspects of the mechanisms of salt movement and diapism from both source layers in this part of the basin. So my talk is basically an overview of these two papers out of the salt tectonics part of my PhD thesis. I'm not gonna talk about the other tectonic structures and deformations that have affected this part of the Persian Gulf. I'm showing only the things that have been published or have been submitted by ourselves and are currently under review. So the first one at the left is a paper that is published recently in Basin Research, and the second one to the right is currently under review. The second one to the right uses seismic interpretation, cross-section restoration plus physical modeling, while the one that has been published uses seismic data and cross-section restoration. So I'm not going into much details about the concepts of salt tectonics, just for introduction, that the salt structures can be very complex in 3D dimensions, but most important salt structures in 3D dimension or map view are elongate or equant in shape. So and include salt walls, salt anticlines, salt pillows, and salt stocks, among the others. So to distinguish that a given diapir is either a salt pillow, salt anticlines, stock, or wall, we have to look at it, its shape in 3 dimension and map view, if it is elongate or roughly equant, and also at the cross-section view to distinguish between the salt, for example, salt anticlines and salt walls. The difference is that the salt stocks and salt walls have a discordant relationship with the overburden, while the salt anticlines and salt pillows show a concordant relationship with the overburden. So these salt structures can be formed from the authochthonous salt layer. The authochthonous salt layer is this level, the original depositional level of the salt, or from the allochthonous salt level, which by definition is a sub-horizontal to moderately deepening salt body in place at higher stratigraphic levels above the autochthonous salt. So when the salt is evacuated from any of these positions, the autochthonous level or a diapiric stem or the allochthonous salt level, it forms a salt well. So the primary salt wells form at the autochthonous level, while the secondary salt well formed at the diapiric stem or the feeder of the diapir, and the tertiary well forms when the allochthonous salt is evacuated into secondary or second generation salt diapirs. So my study area is this part of the Persian Gulf, the easternmost part of the Persian Gulf, which itself is part of the Arabian Plate and is located to the northeast part of the Arabian Plate. So the Arabian Plate itself is surrounded by three main tectonic plates: the Eurasian plate to the north, the Indian plate to the east, and the African plate to the south and west. So I'm going to show a zoom in of this blue polygon. This is a general structural map of the Zagros and Persian Gulf, showing the distribution of the salt structures and salt basins and major fault systems. So this pink polygon, which is quite regional, is the boundary of the Hormuz Salt Basin in southern Iran and Arabian countries to the south of the Persian Gulf. And this small yellow polygon is the boundary of the Fars Salt Basin, which is quite small. So geodynamically, the Zagros is the result of the closure of the Neothetis Ocean that originally separated the Arabian Plate to the south from the Eurasian Plate to the north. And the study area, and this map, which shows the study area, is a zoom in of this blue polygon. So this is my study area, showing different salt structures. These red polygons are emergent diapirs from the Hormuz Salt, and these green polygons are those structures of Hormuz Salt that are buried and are not emergent and surface. And these black polygon, these blue polygons in these two areas show the structures of the Fars Salt in form of salt pillows and salt anticlines. So as you can see, this area in the south of the eastern Zagros and to the west and northwest of the Oman mountains has got a lot of fault systems, especially in this part which we call Strait of Hormuz. And these are the wells that have been drilled in the study area. So we have used these wells to define the seismic horizons in the seismic interpretation. And I've not shown here the distribution of the seismic lines, but all these parts of the basin and the rest of the basin to the west is covered by a regular grid of 2D seismic profiles in two directions, in this direction and this direction, with a spacing of 2 kilometers by 2 kilometers. So it's quite dense. This is a general stratigraphic chart and major tectonic events that have affected the eastern part of the Persian Gulf. So according to this chart, two salt layers are responsible for diapirism in this part of the basin. The first one, which is regional in the Hormuz Salt, which is Ediacaran, early Cambrian in age, and the second one, which is local, is the Fars Salt, which is Oligocene, early Miocene in age, and is time equivalent of the Asmari carbonate, which is quite well known in the petroleum system of the basin. It's a famous carbonate reservoir. So this column shows the seismic horizon that we have defined in the work. The wells in the study area just drilled this part of the stratigraphy. So we have used the wells to define the seismic horizon. For these two seismic horizons in the Permian and Triassic interval, we have used the other wells in the central Persian Gulf and tried to follow them on seismic lines toward the study area. And additionally, we have interpreted 3 other seismic horizon inside the lower Paleozoic interval. We haven't got any age constraint for these reflectors, and the 2 deepest ones correspond to the top and base of the Hormuz Salt, which I will show you how we have defined them in the next slides. And just to for the people who don't know, the Hormuz Salt Basin is called Ara Salt in Oman Salt Basin. They are time equivalent to each other. And this column shows the main tectonic events affecting this area from the late Precambrian to the present day, including extensional collapse and rifting, leading to the deposition of the Hormuz evaporites. And then we have got the passive margin. During the late Permian and Triassic, we have got the rifting and opening of the Neo-Tethys Ocean. But the most important tectonic events affecting this area occurred since roughly Middle Cretaceous in response to the abduction of the ophiolites and emplacement of other thrust sheets, leading to the development of foreland basins. And finally, in the late Cenozoic, we have got the final uplift of the Oman Mountains and Arabia-Eurasia collision and Zagros origin. So in these few slides, I'm going to show you the general structure of the central and eastern part of the Persian Gulf. These two seismic lines show the general structure of the central Persian Gulf. As you can see, this part of the Persian Gulf is marked out by a mega regional basement high or paleo high, which is quite clear here in this part of the seismic line. And in both sides, we have major depot centers containing salt structures from the Hormuz Salt and associated with thickening of the sedimentary cover from the paleo high toward both flanks. And in the northeast direction, we can see a deepening of the seismic reflectors toward the north, toward the Zagros fold and thrust belt, and thickness variations of the late Cenozoic intervals from here to the present day in the foreland basin of the Zagros. So this seismic line is approximately the previous seismic line, but this one also shows the deeper part of the basin. As you can see, the basement of the Persian Gulf is affected by deep-seated extensional faults, which are believed to have formed in Precambrian and controlling the position of the Hormuz evaporite. As you can see, it's quite seen above the paleo high and is thicker toward both flank, forming the salt diapies and these salt pillows. But the eastern part of the Persian Gulf is much more complex due to the presence of two salt layers. The deeper one is Hormuz salt at somewhere at these levels, and the shallower one is the Fars Salt, which is here, both forming salt structures. And in addition, toward the easternmost part of the area, we can see a lot of faults leading to the uplift of this part of the basin and extensive erosion. But I'm not going to talk about these structures. So as I showed you before, the Fars Salt basin was quite local compared to the Hormuz Salt basin. These two figures show this one shows a correlation between wells along this line of section. As you can see, the thickest part of the Fars Salt is in the center of the basin, and it gets thinner toward both east and west, and eventually it shows a thickness, a facies change to the asmaric carbonates. And this seismic line also shows the boundary between the Fars Salt, which is evaporite, and the asmaric formation, which is carbonate. So for the top and base reflectors of the Hormuz Salt, because it's quite deep and it's not penetrated by any of the wells, we have got just few locations in the central part of the Persian Gulf where we can see divergence of the reflectors and at this depths, and we have interpreted this divergence as showing the top and base reflectors of the Hormuz Salt. So we specifically used this line and try to follow the top and base reflectors of the Hormuz Salt toward the study area, because as you can see, the line is very close to the western termination of the study area. So in order to be more focused on the seismic expression of the salt structures and salt tectonics in the area. I have divided the salt structures in this part of the basin into two groups. The first one includes the salt structures outside the Fars Salt basin. This orange polygon shows the boundary of the Fars Salt basin. So the ones that are outside the Fars Salt basin are here and includes 4 salt structures. I'm going to show you 3 of them. And the ones inside the Fars Salt basin are related to the Hormuz Salt, only to the Hormuz Salt, or related to the interaction of the Hormuz and Fars Salt horizon, or as salt pillows. So the first one outside the Fars Salt basin is the Hormuz Salt diapir, which is quite famous. It's probably the most famous salt diapir in the Zagros and Persian Gulf, because it's the location of the Hormuz Salt's first stratigraphic description by Pilgrim in 1908. As you can see, according to these maps, it's exposed in the core of this island with the same name. Most of the surface of the island is covered by salt, by Hormuz salt, but in the southern part of the diapir, there are some outcrops of the Miocene, Middle Miocene and Pliocene rocks that show thinning and diapir-derived debris at the contact with the salt, showing an evidence of Miocene and Pliocene rise of the Hormuz salt. The other point is that according to this cross-section, which is in this along this line of section, this diapir has been defined as a mushroom-shaped intrusion of Hormuz salt by Talbot and his colleagues, with the greatest extent of the salt to be at surface. But let's have a look at the seismic data to see what really this diapir looks like at subsurface. Okay, because the seismic data acquisition has been marine, so unfortunately we don't have any coverage of the seismic data about this island and the other ones in the study area. And this doesn't allow us to see the real geometry of the diapir at depths. But what we can see is that along, for example, this line, the salt, the Hormuz salt, is visible at shallower depths, with the greatest extent of salt in Paleogene levels, which is quite here and is known as the pub deformation. So the greatest extent of salt here, and it gets narrower toward the surface, but it completely disappears at depths. So this one suggests that the stem of the diapir is quite narrow at depths, and the diapir has got a widening upward shape toward the shallowest depths. The other two on to the southwest of the Hormuz island includes the large salt structure, which is this one, and in the seismic data is this one, and another one to the southwest that we have called it West Large Salt structure. So the large salt diapir is very similar to the Hormuz salt diapir, as Ganser has called it a gentler replica of the Hormuz diapir, just according to the surface data. But in the seismic data, crossing the margin of the diapir, again, we see the greatest extent of the salt in form of a salt sheet in the Paleogene level. And toward the surface, it gets a little bit narrower, but it's probably very narrow at depths, but we don't know if it's quite welded, is closed or not. But since we have got some fresh salt at surface, it's possible that the stem of the diapir is not welded. But for the West Lorax, since it's subsurface, as you can see in this map, all these thin black lines are the seismic data. So we have got a good coverage of the seismic lines across this salt structure. This one at shallower depths, as you can see in this map, has a ring geometry surrounding a a secondary mini basin, and at depths we don't have any evidence of salt at these levels, except for some geometries, including this sharp juxtaposition of sedimentary layers against each other. So we have interpreted this zone as a secondary salt well after the salt in the diapiric stem has been closed by some mechanism. We'll look at them later. And here you see the boundary between the Fars Salt and the Hormuz and the Asma'i Formation unlapping the flank of this salt structure. So we can definitely say that this salt is sourced by the Hormuz salt, but it's an allochthonous salt sheet that has been evacuated to form a tertiary well. So the second group of salt structures is those inside the Fars Salt Basin, including some isolated diapies of Hormuz salt in the study area. Includes two roughly circular salt stack. One of them is called Lesser Tomb Island, which is here. And these two seismic lines just cross the margin of the island and this salt stack. So this salt diapy is one of those that has got a lot of challenge as to the source of diapism, if it is from the Hormuz salt or from the Fars Salt. For example, this study by these authors have considered it here to be sourced by the Fars Salt, but according to the seismic data interpretation, we don't have any evidence of Fars Salt flow around this salt stock. This one is another salt body which is not related to the Lesser Tomb salt stock, and I will show you later. But at depths, at greater depths, we don't see the real geometry of the diapir, because again, the seismic data is offset by about 3 to 4 kilometers from the diapiric margin at this island. But probably this slight thickening of the Paleozoic and Mesozoic sedimentary intervals just beside the diapir record some periods of salt movement from the Hormuz salt. So there is no doubt that the source of diapirism in this structure is Hormuz salt. The other one that is totally from the Hormuz salt is called Namakdan salt diapir, which is located to the western termination of the Kashmir Island. And this seismic line is probably the one that has been used by Marcos Nidero and his colleagues in a paper published in 2019. As you can see, this diapir also has got an upward widening shape with the upturn of the Paleozoic and Mesozoic sediments toward the flank of the diapir, and no evidence of the Fars Salt. You can see that no evidence. There is no evidence of the Fars Salt toward or away from this diapir. So the upward widening geometry of this diapir probably suggests some squeezing during the Zagros orogeny in late Cenozoic or from middle Miocene onwards. And also we can see some small salt wings showing extrusion of evaporites from the top of this diapir during these time intervals. So the second group of those that are associated with the interaction of the Hormuz and Fars Salt horizons, they include three areas. The first one is the Abu Musa area, which is here. The Abu Musa itself is an island with the same name. So in general, the structure of these these groups of salt structure is characterized by a circular salt stock at the center and an array of salt walls and salt anticlines around it, as you can see in the seismic data. So this is the central salt structure, and this one are the surrounding salt structure. The surrounding salt walls and anticlines are totally from the Fars Salt because the base of the salt and the older sediments are quite continuous. But for the central salt structure, it has got a detail to the source of diapirism, For example, these authors have considered it to be totally from the Fars Salt, and they said that because they have not been able to see any halokinetic sequences at the Mesozoic and Paleozoic intervals, so they have considered it to be sourced from the Fars Salt. And I'm not at all surprised that they have not been able to see any halokinetic sequences at these depths, because the seismic lines is offset by about 4 kilometers from the island margin, and possibly by 5 kilometers from the diapiric margin at depths. But by definition, the halokinetic sequences are observed only up to 1,000 meters from the salt contact. So it is not surprising that they have not seen them. But we have used exactly the same seismic line to investigate the source of diapirism in the central salt structure. So to address this question, we have got three lines of evidence. The first one is looking at the geometry and thickness of the overburden around this salt structure. So as you can see, there are some thickening of the Mesozoic and Paleozoic sediment just around the diapir within this main basin. The second point is that in this level, which is at the Paleogene level and older than the Fars Salt, as you can see in this zoom-in image, you can see a divergence of the seismic horizons just above and below of this transparent zone that we have interpreted it as showing an allochthonous body of Hormuz Salt, because it's in place at older stratigraphic levels compared to the Fars Salt, which is here. And the third point is that there are a lot of volcanic rocks exposed in the island surface. So these volcanic rocks are derived from the Hormuz Salt, and it is not only unique to this salt structure, it's found in many of the salt diapirs in the Zagros and Persian Gulf. According to the well data, the Fars Salt, because the Fars Salt has been drilled by a lot of wells in the study area, according to the well data, the Fars Salt is much more pure and it's devoid of any volcanic rocks and other sedimentary blocks. So we conclude that this salt structure is primarily sourced by the Hormuz Salt, although we may have got some flow of the Fars Salt toward the margin of the diapir, because according to the seismic line and detailed interpretation of the reflectors, we see that the Fars Salt deposited in Oligocene to early Miocene started to flow shortly after deposition. And at the first stage, according to the deposenta actual traces, at the first stage, we have got an important quantity of salt flow toward the central diapir, but at the later stage, according to the overburden geometries, we have the mini basin migration toward the surrounding salt structure with the source by Fars Salt. And this migration of the mini basins due to welding of the Fars Salt basin formed some structures that are similar to the expulsion rollovers, and they are salt evacuation mini basins. The second example is a greater tone salt structure in this part to the northeast of the previous example, which is in general similar, characterized by a central salt structure that is very much complex, and an array of ringed salt walls and salt anticlines from the Fars Salt. So as you can see, different authors have interpreted it in different ways. It has been considered to be sourced from the Fars Salt only, or by the contribution of the Fars Salt and Hormuz Salt as well. But recently, Stidero et al. 2020 have used seismic data around the salt structure and defined different geometries and different salt structure. They have defined the central salt structure as being sourced mainly from the Hormuz Salt. and associated with the allochthonous salt around the diapiric stem at shallower level. This is the allochthonous salt sourced by the Hormuz Salt. And according to the thickness change in the Paleozoic and Mesozoic intervals, they have defined this area in the southern part of the central diapir as being a secondary mini basin. So we have used the same data and we try to interpret in detail the central salt structure, but for the southern part of the diapir, which is quite complex, we are not sure if it is actually a primary mini basin along a southern irregular boundary of the central diapir, as shown in this line, in west-east line, or it is a secondary mini basin due to the collapse of the diapir. And if it is a secondary mini basin, we have defined it as an encased bucket mini basin flanked by bucket wells. But what's quite clear is that we have got, again, allochthonous Hormuz salt at Paleogene levels older than the Fars Salt. So we're quite sure that the source of the central salt structure is primarily from the Hormuz Salt. And if you look at the geometry of the overburden, especially we have got a thickening of the Jurassic interval just toward the central salt structure. So that's why if you consider this southern area as a secondary mini basin, we think that it's formed by the collapse of the central salt structure, likely because of welding of the salt layer as shown by the shifting of the depot center toward the salt diapir. You can compare this with this schematic illustration by Frank Peel to see how the daughter basins or secondary mini basin can form about the diapir after the allochthonous salt is welded. So the third area is called the Hengam area or Hengam salt diapir, just to the northeast, close to the northeastern boundary of the Fars Salt. So even if the Fars is thinner compared to the central part, it shows evidence of flow, but it doesn't show any evidence of ring salt structures around the central diapir, as we saw them in the Abu Musa and Greater Tomb area, but here in the case of the Hengam, we don't see them. But we do see the evidence of Hormuz and Fars Salt flow toward the central salt structure. We do see the welding and evacuation and welding of the Fars Salt, and in addition, we can interpret an allochthonous salt sheet of the Hormuz Salt, again in the Paleogene level, which has been subsequently evacuated to form a tertiary well, and most of the salt sheet has been evacuated toward the main diapir that is primarily the source of the allochthonous salt sheet. And the third group of the structures inside the Fars Salt basins are shallow Fars Salt pillows overlying deep Hormuz Salt pillows, as you can see in these two seismic lines. A shallow Fars Salt pillow at these depths, and here it's quite a gentle inflation of the Fars Salt overlying a deeper pillow of Hormuz Salt. So as you can see in these two examples, we have got the thinning of the oldest overburden of the Hormuz Salt toward the top of the pillow, which gives us some indication of the earlier history of the Hormuz Salt movement. So, and now I'm going to show a few examples of the cross-sections that we have restored across these structures inside and outside the Fars Salt basin. The first one is a cross-section across the Abu Musa salt structure, which is here. So according to the restored cross-section, the earlier history of diapirism is associated with the rise of Hormuz salt in passive diapirism manner during the Paleozoic and Mesozoic, followed by extrusion of evaporites in the Paleogene, And then we have got the deposition of the Fars Salt and its flow since early Miocene. So as you can see, according to the restored cross-section, since from this stage onwards, firstly, the Fars Salt has flowed toward the salt diapir, the central salt diapir mainly, and once it has been welded just close to the central diapir, the depot center has migrated outward toward these peripheral salt structures to feed the Fars Salt into this diapir. So the final geometry that we have got is the welding of the Fars Salt and the development of these salt walls around the central salt structure. And the mini basin above the Fars Salt contains these migrating depot centers toward the peripheral salt walls. The second example is a cross-section across the tectonic salt pillows. So as you can see again, the Hormuz salt started to flow shortly after deposition, and the pillow was growing throughout the Paleozoic with some quiescence during the Mesozoic. As you can see, these three layers that are Mesozoic intervals show a little bit of thickness change, but roughly it's constant thickness. So we interpret it as showing that the salt pillow has not been growing anymore. And it's followed by the position of the Fars Salt and gentle inflation of the Fars Salt just above the salt pillow as the sediments were deposited above the Fars Salt and imposed load on it. And two other cross sections are across the salt structure outside the Fars Salt basins. One of them is across the Larak salt structure, and the other one is across the West Larak. In this one is across the Larak, and this one is across the West Larak. So overall, the evolution of the diapir during the Paleozoic and Mesozoic, as you can see, is quite similar for both salt structure, with the exception that in the case of the West Larak, it is a salt wall developed above a basement fault deeping to the west. And for both of them, since late Cretaceous and especially in the Paleogene time, we have got extrusion of evaporites forming a salt sheet, which is asymmetric in the case of the West Larak and quite symmetric in the case of Larak. The other, and since Oligocene, we have got the squeezing of the salt structure and uplift of the area, followed by erosion and extrusion of evaporites to the surface, as we can see in the Larak Island today. So in addition to the symmetry of the salt sheet in the Larak and its asymmetric shape in the West Larak, the other difference is that the salt sheet in the case of the West Larak has been subsequently loaded and evacuated to source this secondary salt structure, which is in form of a ring salt wall in 3D space, and in 2D it's characterized by two bodies of salt separated by this secondary mini basin, which is a dish mini basin. So as to the source, to the mechanism triggering or driving the development of allochthonous salt, we have this paper by Mark Rowan in 2017 on the allochthonous salt. So he has defined three mechanisms responsible for development of allochthonous salt, including a decrease in sedimentation rate as compared to the salt rise rate. Or there should be a contractional squeezing of the diapir, which is a quite well-known mechanism. The third one is the development of expulsion rollover structures in the hanging wall side of the leaning diapir. So in the case of our examples, we haven't got any evidence of expulsion rollovers in these sediments, the late Cretaceous and Paleogene sediments. Nor do we have any evidence of a decrease in sedimentation rate. So the only mechanisms that could have been responsible for the development of allochthonous salt is a contractional squeezing of the diaphragm, leading to the welding, to the secondary welding of the diaphragm stem. So now I'm going to show you two physical models that we have done in the Geomodels Research Institute of the University of Barcelona to investigate some interactions of the Hormuz and Fars Salt horizons and the kinematics of salt flow. So for this, you can see here the setup of those physical models. It's model 1 and this one is model 2. As you can see, it's quite similar. For the Hormuz and Fars Salt layers, we have used two layers of polymer with the same properties but different color. This blue polymer shows the Hormuz salt at the base of the model, which is almost welded. And the green polymer shows the Fars Salt, which is limited, as we can see in the nature. So the difference between model 2 and model 1 is that in model 2, we have shifted these salt pillows in the Hormuz level by 10 centimeters toward the hinterland to see its response to contractional deformation. So in these slides, I'm going to show you the evolution of the diaphragm after the establishment of the upper polymer, which is the Fars Salt, and its lateral sand. So as you can see, after putting the first overburden sand layer above the Fars Salt polymer, we have applied contractional deformation. And the contractional deformation coeval with sand deposition led to the squeezing of the salt stock, as you can see here, from the very beginning of the shortening due to layer parallel shortening of the sand layers. But we don't see any evidence of macro scale contractional structures like fold and thrust. But at this stage, the contractional structures start to develop. And finally, at the end of experiments, we have got a box fold in the hinterland bounded by thrusts and back thrust that didn't reach the salt structure in the foreland, but we have got the extrusion of evaporites from the salt stock, from both polymer layers from top of the salt stock. And as you can see, we have got the translation of the salt stock toward the foreland in response to contractional reactivation. And this model 2. So in model 1, as you can see, we don't see any evidence of the upper polymer flow, except minor evidence of polymer extrusion at the flank of the salt stock. So in order to test to see if we can reproduce some salt structures of the Fars Salt as we can see in nature, after the first overburden layer above the Fars Salt polymer, we vacuumed off the sand along this ring strip around the salt stock, and then we applied shortening as we added more sediments, more sand layers to the model. So this vacuuming of the sand imposed a differential loading on top of this green polymer, which allowed the rise of the polymer along this ring salt walls. And at the later stage of the experiments, we have the extrusion of evaporites from both salt structure, from the central salt structure and from these ring salt structures surrounding this salt stock. And finally, we have got these box fold bounded by these thrust folds. The difference between this model and the previous one is that in the case of model 2, the box fold shows a greater amount of shifting toward the foreland, likely due to the presence of this deep-seated salt pillow. So after the end of both experiments, we have cut the model into closely spaced 3 mm spaced cross sections, and we use those cross section to reconstruct the 3D structure of the model to be able to see its interior structures, and allowing us to produce any cross section in any direction and depth slices. So we have converted the 3D, the constructed 3D model into a seismic volume. So as you can see, in the case of Model 1 cross-section, we don't have any evidence of reactivation of the deep-seated pillow, which was at this part of the model. And in the case of the southern part of the model, which is the salt stock part of the model, we have got the extrusion of the lower polymer in the center and some rising of the upper polymer in the flank of this central salt stock. And in addition, as you can see in the cross section, we have a shifting of the box fall and the thrust toward the foreland in this part of the model where we have the salt pillow. So in the case of Model 2, it has some differences. For example, the salt pillow in Model 2 shows reactivation and involvement in the core of the box fold due to its closer position to the hinterland, even if Model 2 has been shortened by about 2 centimeters less than Model 1, but you can see that the salt pillow has been reactivated. And in the case of the upper polymer, as you can see, we have got these isolated salt structures from the upper polymer, and we have the flow of the upper polymer in the flank of the lower polymer. But an interesting point is that even if after significant extrusion of the polymers, we don't see any evidence of mixing of both polymers. So this example led us to interpret the seismic lines in the study area in the way that the Fars Salt has been rising at the flank of the Hormuz Salt without mixing with it. And around these isolated salt structures of the upper polymer, we have these shifting depositors and primary wells, as we can see in the natural examples in the seismic lines in our area. So in this slide, I'm going to, in this one and the next one, I'm going to show you the internal structure of both models. We are looking at the different depth slices of both models. This is the 4 depth slices of Model 1. So as you can see, the box fold is quite linear at shallower depths, but at greater depths toward the base of the model, it shows a shift toward the foreland in this part of the model. So the interesting points about the salt structure is that in the case of the salt pillow and the salt stock, they show forelandward translation due to shortening of the model. But as you can see, this is the final geometry of the salt pillow, and this one is the original geometry of the salt pillow. So it doesn't show any change in the shape of the salt pillow because it has not been reactivated during shortening. But in the case of Model 2, in addition to the translation of both salt structures toward the foreland, we have this change in the shape of the salt pillow due to the contractional reactivation of the pillow in the core of the box fold. And we have got a larger amount of forelandward shift of the box fold in this part of the model. So it shows that the location of the salt structures compared to the hinterland, which is this part, can influence the development of the location and development of the contractional structures as we can see in the northern part of our study area and in the Zagros. So, from the interpretation of the seismic data, cross-sectional restoration, and these two physical models, we can see three main stages in the history of the Hormuz Salt movement in the study area, which includes an early stage of past diapirism during the Paleozoic and Mesozoic, followed by contractional squeezing of the diapirs leading to the extrusion of evaporites. And since Oligocene, we have passive diapirism and contractional squeezing due to the shortening of the diapirs in response to the orogenic belts to the north and east of the study area. So the contractional deformation responsible for the extrusion of the evaporites in Paleogene is constrained by two lines of evidence, including, firstly, in the study area, folded and unlapped wedges in the Paleogene pub deformation, as you can see in these seismic lines. So these folded and unlapped wedges show that there was a contractional deformation affecting this part of the basin. And in addition, in Oman, recently, these authors have used low temperature thermochronometry cooling aids of apatite and zircon crystals from this area, Jabal Akhtar culmination from Oman, and identified a rapid phase of rapid exhumation and uplift of the Oman mountains in late Eocene, around 40 or 42 million years ago. So this low temperature thermochronometry data and these seismic examples show that there was a contractional deformation affecting the Oman mountains and Zagros and squeezed the diapirs in our study area. So a main question is that when did the earliest movement of Hormuz Salt occur? So these seismic lines have been available just at the beginning of the current century. So before the advent of these seismic lines, most researchers had the idea that the Hormuz Salt was first mobilized in Mesozoic and no earlier than Permian. But these seismic data allowed the researchers to identify all the phases of salt movement according to the changing thicknesses of overburden and thinning of these Paleozoic intervals above the salt pillows. And in addition, in Oman salt basins, where the equivalent R salt is shallower and is drilled by wells, and also is quite well imaged in seismic lines. As you can see, the first overburden layers above the R salt shows evidence of thickening and thinning about the R salt, indicating that the R salt started to flow quickly after the end of deposition of the evaporites. And there's also evidence of earlier phases of salt movement, of Hormuz salt movement in northeast part of Saudi Arabia, where again we have got a shallower depths to the Hormuz salt, and these Cambrian and Ordovician strata are constrained by wells. So as shown by Stewart in this paper, these Cambrian sediments, as you can see, show thinning toward the top of these salt pillows, indicating that the salt, the Hormuz salt, flowed at Cambrian times. Firstly, so in our study area also, if I showed you these seismic examples before, and the evidence that we have got for the earlier history of Hormuz salt, according to the thinning of this overburden, is compatible with the published examples from Saudi Arabia and Oman salt basins, indicating that the Hormuz salt started to flow at Cambrian. So in the case of the Fars Salt, according to the seismic examples and cross-section restoration, as I explained before, and the physical models, the main mechanism that drove the Fars Salt movement was differential sedimentary loading, the gravitational loading, because as we saw in the first physical model, we didn't apply any gravitational load on top of the Fars Salt. We didn't see any evidence of a formation of isolated diapies of Fars Salt. So the main mechanism was differential sedimentary loading, but at later stage, Zagros shortening could have squeezed the Fars Salt structures and increased the salt rise rate. So we have seen that the Fars Salt in the Eastern Persian Gulf has flowed only where it has interacted with a major diapy of Hormuz salt that extruded allochthonous salt at the Paleogene level. So according to this observation, we have proposed two scenarios based on the fluid mechanics concepts in salt tectonics when salt is considered as a viscous fluid. So we have considered two scenarios. The difference between them is the extent of this allochthonous salt sheet of Hormuz salt. So one scenario with a larger and possibly thicker salt sheet, and this scenario with a smaller and likely thinner salt sheet. So we have got the evidence of evacuation of that salt sheet in the seismic lines. So we interpreted that after its emplacement, the salt sheet has been loaded and started to flow toward the main diapy. So this evacuation of the salt sheet allowed a change in the geometry of the Fars Salt, and this change in the geometry of the Fars Salt imposed, according to this concept, imposed a gradient in pressure head and elevation head on top of the Fars Salt. So as the Fars Salt was subjected to lateral pressure gradient, it was evacuated and flowed toward the central salt structure in the same way as the underlying salt sheet. So finally, we've got the welding of the salt sheet and almost welded Fars Salt, and we have these shifting depot centers toward the salt diapy. And in the second scenario, where the salt sheet is small and possibly thinner, this smaller extent of the salt sheet didn't allow an efficient of its evacuation, but probably its slight evacuation was enough to change the geometry of the Fars Salt and impose a pressure head and elevation head on top of the Fars Salt. So when the Fars Salt was subjected to differential load, it started to flow toward the central salt structure at earlier stage. And once it's welded out in close locations, in locations close to the central diapy, the depot center migrated outward to the areas where we have got Fars Salt in the pedestal of this salt structure. And this increased rate of salt supply to the salt structure led to this diapy to break through its roof by active diapirism and its evolution into a passive salt wall. But at the end, once the Fars Salt was welded out in both sides of this salt structure, it was buried by sediments and was only affected by Zagros contraction, leading to the arching of its roof. So to recap what we have got in this area in the Persian Gulf about the salt tectonics, the Hormuz and Fars salts began flowing at Cambrian and early Miocene respectively, and we have identified three main states in the history of Hormuz salt movement, including a Paleozoic and Mesozoic passive diaperism stage, followed by contractional rejuvenation and extrusion of evaporite at Paleogene and younger times. So the Fars salt was mainly triggered by differential loading, not by tectonic contraction, as suggested by the seismic data and the physical models. And an important point is that the Fars salt was only flowed wherever it interacted with those diapies of Hormuz salt that developed allochthonous salt sheets at Paleogene level. And the direction of the Fars salt flow likely was controlled by the lateral extent and dimension of those salt sheets in place at Paleogene times. So, okay, at the end of my talk, I would like to acknowledge all the institutions and people that have helped me during my studies about the salt tectonics of this area and the Zagros. They include the university where I have been studying, or the Tabiat Madaris University, or the University of Barcelona, where I have been there for a short stay and I've used the physical modeling laboratories. I acknowledge the support by IOC that provided the seismic data for this study, and petroleum experts for providing the MOVE software to the University of Barcelona, where I've used this software for cross-section restoration. And I would like to thank AAPG Salt Basin for inviting me to present my work, and the panelist team for organizing these webinars. And also I acknowledge my co-authors during my studies. I'm grateful to Ali Asagi, my PhD thesis supervisor, and Josep Anton Munoz and Salman Jahani, advisors. I'm grateful to Oriol Ferrer and Pablo Santolarga, who have helped me with the physical models, and Mohsen Said Ali with the interpretation of the seismic data. I'm also grateful to Nuria Carrera, who is not listed as a co-author on my papers, but helped me with the setup of the physical models. And finally, I would like to thank my salt tectonics teacher. I started the salt tectonic with someone from National Iranian Oil Company. And during my PhD, I have been benefited by the excellent knowledge of Josep Anton Munoz and Oriol Ferrer from the University of Barcelona. But I also would like to acknowledge that I would like to thank Mark Rowan, who constantly taught me salt tectonics since I was a master's student, and also during my PhD. Thank you.
Great, Jafar. Thank you so much. That was an awesome talk. I really enjoyed your work. Let's see here. We have a bunch of questions from the audience. Are you, do you have time to go through the questions?
Yeah, no problem.
Okay.
It's my pleasure.
Okay, good. Okay, so I will start. There are a few questions in the chat, so I'll start there. If anyone has any other questions from here on out, can you please put it in the Q&A box, which is located on sort of the bottom center part of the Zoom chat window. Okay, so the first one is from Marco. Let's see, his last name is in his Gmail, Snydero, I believe. Thank you for the presentation and for kindly considering our work. 2 questions. So his first question is, you interpret different excursions of Hormuz salt in your structures, including tertiary welded ones. Do you think that this could have a impact or main reason for triggering the Fars Salt movement?
Okay. Yes, as I showed you in the, I think it was the last slide, where we considered two scenarios, including a scenario with a larger salt sheet of Hormuz salt in the Paleogene level and a smaller salt sheet and a smaller salt sheet. In these two scenarios, the evacuations of these salt sheets affect the geometry of the far salt layers, leading to a lateral gradient in pressure head and elevation head on top of the far salt that triggered its lateral flow and diaphysium.
Great. So his second question is, as you know, the upper part of the unit that defined as Fars Salt is composed by about 500 meters thick of mainly anhydrite. This unit does not behave as a mobile unit. It presents downlap geometries close to the tomb diapir. It could be an apparent downlap or eventually a lateral change in facies in proximity of the central salt diapirs. But in any case, it's a tricky interpretation. Do you have any thoughts or ideas about this?
Yes, I agree that that the upper part of the far salt is composed of anhydrite and some likely clay stones, and I've seen those geometries as Marco described as apparent downlaps. But I'm not sure if it is a result of facies change in proximity of the central Hormuz salt diapir. But in some examples, I've seen that even if we consider this part as being the far salt, it's completely evacuated. So possibly showing that even this upper part of the evaporite has flowed laterally into the diapirs of the far salt, even if it was far from the central salt structure.
Okay.
I don't know if I have answered the question correctly.
Yeah, no, I think it sounds, yeah, that was a really good explanation. Thank you for that. Dr. Hudek, he has a question here. You mentioned using exposed volcanic rocks to distinguish between Hormuz and Fars evaporites. Have these volcanic rocks been dated?
Okay, it's a good question. Yes, in the Hangam Island, where we have got evidence of Hormuz and Fars Salt, some of those volcanic rocks have been dated and show the Precambrian age. But this point is not the only one to distinguish between the Hormuz and Fars evaporites. We have used other key evidence along the seismic lines to interpret the central salt structure may be made of Hormuz and Fars Salt. So the presence of volcanic rocks is only one of those key points. And yes, they have been dated and they show Precambrian age. And also in wells, I think about 5 or 6 wells have drilled the Fars Salt and they don't show any evidence of volcanic rocks in the Fars Salt interval.
Okay, cool. That's very interesting. Dave Waters, he says, many thanks, Jafar. Very enjoyable talk. Ahmad says, thank you for your presentation. It was late. He was late, but he will look for the uploaded one. Okay. And then we have another one. Thank you for your presentation and your detailed explanation. And then one of our panelists, Timothy Shin, he says, hi, Jafar, thanks, and great presentation. In the sandbox models, you did not impose any of the earlier Hormuz salt movement prior to the deposition of the Fars salt. Do you think you could have gotten model results more similar to the seismic you've shown if you would have put those those structural domains
Uh,
on there prior to doing the
Okay,
model?
it's a very good question. Yes, we haven't considered the evolution of the Hormuz salt structures in a passive diapirism manner before the deposition of the Fars salt. But I would say that firstly, we wanted to see the interaction of both salt horizons. So after the deposition of the Fars salt. The other point is that, so we know that there was major diapir during the deposition of the Hormuz salt, a major diapir of Hormuz salt during the deposition of the Fars salt. So we constructed this diapir of Hormuz salt manually, ignoring the passive diapirism history of the diapir. So, and the second point is that we, from the cross-section restorations and other works previously published, we know that at about Miocene or Oligocene times, most of the Hormuz salt around these diapirs have been welded out. So that's why we know that during the deposition of the Fars salt, we have got the welding of the Hormuz salt, so it doesn't affect the history of the Fars salt movement. The only thing that we know is that the main diapir of Hormuz salt was present during the deposition of the Fars salt, and we have considered it in the physical models. Okay.
Great. We have a couple more. Are you still good to keep going?
Yes, keep
Okay.
going, please.
Great. Okay, so Dr. Rowan, he says, hi, Jafar, great talk. The Hormuz distribution was controlled by the NS basement architecture. I think he means north-south basement architecture. What topographic relief controlled the distribution of the Fars, and did the Hormuz diapirism play a key role? So yeah, I guess this question is somewhat related to Tim's.
Yes, thank you, Mark. It's a very good question. And we have considered it in the papers. For the sake of time, I didn't go into much details about these points. But according to the seismic data, firstly, about the Hormuz salt, yes, we know that its deposition has been controlled by mainly north-south basement faults, as I shown in the seismic data at the beginning of the talk. But in the case of the Fars salt, we didn't have any significant topographic relief except for the Hormuz salt diapirs. And as you can see in the seismic data and our cross-section restoration, we have got a thinning of the Fars salt just close to those major diapirs of Hormuz salt. So it means that deposition of the Fars salt has been affected by those diapirs. Yes, you're correct.
Okay, great. Thank you for that. Dr. Juan Soto, he says, good talk, Jafar. Is there a lithological compositional difference between the two evaporite units?
Yes. So the Hormuz salt stratigraphy is known from the salt sheets exposed in the Zagros and in the islands of the Persian Gulf. So they show that the Hormuz salt is very impure. It contains evaporites and a lot of other sedimentary rocks, and also an significant quantity of volcanics and metamorphic rocks. So this is the stratigraphy or composition of the Hormuz salt. But the Fars salt, as it is drilled by wells in the Persian Gulf, show a more pure stratigraphy as compared to the Hormuz. It's very pure at the basal part. But at the upper part, as Marco mentioned, it's impure, including halite, anhydrite, and claystone. but it doesn't contain any volcanics and other blocks of sedimentary rocks, as we can see in the case of Hormuz.
Great, thank you for that. That concludes our questions. We have one more comment from Majid Alipur. He says, "Thank you, Jafar. Very impressive results. Congratulations." So yeah, that concludes our talk. Thank you so much for being here. We really appreciate that you're able to present to us, and please be a lookout. We will put this recording up on YouTube, and if anyone in the audience has any further questions, please feel free to email us and we will forward your questions to Jafar.
Yeah, I would be happy to answer any other questions. I will be happy to answer them through emails. And thank you for inviting me to present my work.
Absolutely. Great. Have a good day. Take care.
Have a good time.
Bye-bye.
Bye.